So you have a Chapter 3 test this weekend on My Math Lab. It's going to be available starting tomorrow, Friday, and it's going to be available until Monday, 11:59 p.m. So you want to be able to get on and take this exam on My Math Lab this weekend. You want to be able to sit down and do it in one sitting. You won't be able to get back into it. So you can't leave and get back in and finish it. If for some reason you do not like your score, you didn't do very well, and you want to retake it, you have three chances to take this test. So if you retake it, you will be submitting your written work, or if you take it, you're going to be submitting your written work. You're going to turn in the highest grade. So turn in the work for the highest grade you got on My Math Lab. So today I just want to spend time just reviewing everything that we've covered so far in this course over Chapter 3. And so let's get started. So I'm just going to read through this because I feel like this is pretty good. So in this chapter, let's see if I can highlight it at the same time. Okay, so in this, no, I guess I can't. Let's try this. There we go. Maybe with my pen. Let's start this again. So in this chapter, we've introduced the idea of limit and continuity of functions, and then used these ideas to explore calculus. We saw that the difference quotient can be represented in the following way. So we've talked about the difference quotient being the average rate of change. We talked about it being the slope of the secant line and the average velocity. We also saw that the derivative can represent the instantaneous rate of change, the slope of the tangent line, and the instantaneous velocity. We also learned how to estimate the value of the derivative using the graphical differentiation. And the next chapter, which we'll be getting to and started on, we will take a closer look at definition of derivative to develop a set of rules to quickly and easily calculate derivative of a wide range of functions without the need to directly apply the definition of the derivative each time. Okay, so for this chapter, we have to use the definition of the derivative. So we cannot use those techniques right now when you're taking this exam to make it easier to take the derivative. We need to use that formal definition. And we'll go through more examples of doing that today. So first thing that we looked at in this class was a limit of a function. And in order to look at limits, let f be the function and a and l be real numbers. Number one, as x takes closer and closer, but not equal to a on both sides of a, the corresponding value of f of x gets closer and closer, perhaps even equal to a. So this is where we were looking at, if we're coming in on the left and the right of a, we have to be coming into the same value. And in this case, this would be L. 2, for a limit, the value of the function f of x can be made real as close to L as desired by taking values of x close enough to a, then L is the limit of f of x as x approaches a. So, and we wrote that notation that as the limit x goes to a, f of x over L. So we saw that also limits, it actually didn't have to be defined at x equals a, and we could get a limit. So for instance, in this case, if we had an open circle instead, this would still be approaching L as x got closer and closer to a on the left and the right. You might even have a point below where it's defined, but the limit is still L. So you should be able to look at a graph Given a graph, you should be able to find limits, and you should be able to tell if it exists and what it is, and if it doesn't exist and why. So this brings us to the existence of limits. So the limit of f as x approaches a may not exist. One, so if f of x comes infinitely large in magnitude, positive or negative, as x approaches the number a from the left or right, we write it as a limit as x approaches a equals infinity, or the limit as x approaches a of f of x equals negative infinity. Even though we say that goes to positive or negative infinity, the limit does not exist. So in this case, this is where we had a vertical asymptote at a. And as we were coming in, getting closer and closer to a, we might shoot off to positive infinity. Could do that on both sides, or maybe one is shooting down to negative infinity, or they both could be shooting down to negative infinity. But that's an example where the limit does not exist. And it's because we have an asymptote, vertical asymptote there. We say if f of x becomes infinitely large in magnitude, positive, as x approaches a from one side, and infinitely large in magnitude, negative, as x approaches a from the other side, then the limit does not exist. So one side, it's getting really large. Actually, that's the case I drew, where it's getting really large, going off to infinity, and then going down to negative infinity. If x is approaching a of f of x equals L, and x approaches a f of x equals m, and Ln does not equal n, then we say that the limit does not exist. Okay, so this is where you would have some jump in the graph. So as we're getting closer to a on one side, we might be getting closer and closer to this y value of L. And then as x is approaching a on the other side, this would be getting closer and closer to m. And so L and m, those y values are not the same, so the limit does not exist. We also looked at limits as x went to infinity and negative infinity. And this is what we use to help determine, is there some value that that is going to? Is there a horizontal asymptote? So as we're going to infinity or negative infinity, we're getting closer to one y value. And there's one rule that helped us. Limits of infinity for any positive real number n, if you have the limit as x goes to infinity of 1 over x to the n, this is the same thing as the limit as x goes to negative infinity of 1 over x to the n, and this is equal to 0. So there were times that we used this fact to help us manipulate a rational function to see if this went off to infinity or negative, if this went off to 0.
Professor?
Yeah.
I have a question. So for where you put a and then one going positive and the other one going negative, does that one have a limit, or the limit does not exist on that one?
The limit doesn't exist because it's not heading towards any one particular y value. Even this as x is going closer to, so let's see, the limit as x is going closer to a on the left of this function here, f of x, we would say that it's equal to positive infinity, but that limit doesn't exist because it's not one y value that it's approaching. Also, the limit as x approaches positive and a on the right of f of x, in this case, this one is shooting downwards to negative infinity. We'd say that's negative infinity, but because it's going to an infinity, not a particular number, we say it doesn't exist. This case, anyways, they would be going to opposite directions. Any other questions on that?
Yeah, I have a question about the limits at infinity. Would you mind drawing out for me how that equals 0?
Yeah.
Either of those? Thank you.
Yeah. So let's look at that. That limit as x goes to infinity, 1 over x to the n. And it really doesn't matter. And it has to just be a positive integer down here. If it was a negative integer, that means I would be bringing it up into the numerator and this wouldn't exist. So
Okay.
it has to be positive, has to be greater than 0. And so if you think about this, just like putting in a table and just trying it and seeing what happens, if we put in, let's say 10 in here, and let's say, well, we got to put a number in here. So it could be any number, 1, 2, any value down here, even a square root. But if I put in, let's say just 1 over x, when I put in 10 here, this gives me 1/10, which is the same as 0.1. If I put in 100 here, 1 over 100, this is giving me 0.01. And so as I'm blowing up, so if I put in 1,000, I get 1 over 1,000. This is even closer to 0.0001, 1,000ths. And so as this number here approaches infinity, as it gets larger and larger, and it doesn't have to be multiples of 10, I could have put in 2,500, 1 over 2,500. I'd have to plug that in my calculator, but that's even getting closer to 0 than 1 over 1,000.
Gotcha. Okay.
And that's why that is going to 0. And so we want to use that fact that 1 over x or 1 over x to some positive power is always going to 0. In this case, this is 0.0004. And so as x is approaching infinity, these y values are going to 0. And so that's the same idea when we're going to negative infinity. These are just would be, if this was -10, this would be -1/10.
Yeah, and it's still approaching 0.
Yep, exactly.
Thank you.
Yep. So you guys want to look at an example right now of that going to infinity? So for instance,
Yeah, I think that would be great.
okay. Let's look at an example using that rule. I want to make sure. Okay. Let's look at the limit. Find a good one, guys. As x is approaching infinity of x squared plus 6x plus 8 all over x cubed plus 2x plus 1. So if we went in and we plugged in infinity wherever we saw an x in here, both the numerator and denominator would be shooting off to infinity. Putting in a large number, squaring it, that's positive, plus 6 times some number getting larger and larger is positive, plus 8 is positive. So I see my numerator is going to positive infinity, and I'm looking at the denominator. Well, cubing a positive number, that's positive, plus 2 times a positive is positive, plus 1 is positive. So I get infinity over infinity. And this is one of those indeterminate forms. And the indeterminate form means that this is not telling us anything. We don't know what the answer is. This doesn't tell me anything about this limit. And so this is where we had to go back and manipulate that function so that when we did take the limit, something would fall out or it wouldn't exist. In this case, when you have a rational function and you get infinity over infinity, what you want to do is you want to multiply by the variable raised to the highest power that you have in the denominator. And so in our case, our variable is x, and I'm looking at the denominator, the highest power is a cube. And so in order to manipulate this, we want to divide every single term in the numerator and denominator by 1 over x cubed. Technically, another way to think of this, we're going to be multiplying, because we can't just divide by something, but we can multiply by 1 and keep it equivalent. And so I'm going to rewrite this as a limit as x goes to infinity of this x squared. I'm going to multiply each term in here by 1 over x cubed, or divide each term by an x cubed in the numerator and denominator. So I would have this x squared over x cubed. Then I would have this plus 6x over x cubed. I would have plus 8 over x cubed, all divided by the denominator, and then all those terms divided by x cubed. So I have this x cubed divided by x cubed, 2x divided by x cubed, and plus 1 divided by x cubed. So if we go back and we use our rules of exponents, same base, x squared and x cubed, we subtract exponents. And I tend to leave it, the higher exponent is in the denominator, then I'm going to leave the variable in the denominator and subtract the exponents. So x cubed is, that degree is higher than an x squared. So I'm going to look at it as 1 over x and then subtract the exponents, 3 minus 2, which is 1, plus 6 all over x divided by x cubed, that gives me an x squared, plus 8 over x cubed. All divided by x cubed divided by x cubed is 1, plus 2 over x cubed. That's going to give me 2 over x squared, plus 8 over x, 1 over x cubed. So now as we're plugging in infinity, wherever we see an x, notice that those x's, most cases, are in the denominator and not in the numerator. And so if we have a number over x, as x is going to infinity, or a number over x to an even power, which all of our cases, positive power, which all of our cases are, we can say that those values in here, 1 over x as x goes to infinity, this would go towards 0. 6 over x squared as x goes to infinity, that hints towards 0. 8 over x cubed as x goes to infinity goes to 0. So this numerator is getting closer and closer to 0 as x goes to positive infinity. Well, we have just this single one, plus, so 2 over x squared as x goes to infinity, this piece goes to 0, and 1 over x cubed as x goes to infinity also goes to 0. So we have this 0 over 1. It's okay to have 0 in the numerator and not in the denominator. So 0 over 1 is a number that is equal to 0. So the limit as x goes to infinity of that function is equal to 0. So another example, as x is going to infinity, we're now looking at 2x squared plus 5 all over 5x squared minus 1. Again, if we go in here, we plug in infinity, wherever we see an x, we get that indeterminate form of infinity over infinity. So we want to go back in and we want to manipulate this. And so one way to do that is looking at the degree in your denominator. So that's a square, or 2, degree 2. And we're going to divide or multiply everything by 1 over x squared, both in the numerator and denominator. Where you use that fact that the limit is some number over x as x goes to infinity goes to 0. So if we distribute that, well, 1 over x squared times 2x squared is just 2, plus 5 times 1 over x squared is 5 over x squared, divided by, so 1 over x squared times 5x squared, x squared's canceled, just leaving you with 5. And then a 1 over x squared times -1 is minus 1 over x squared. And so now if we go in and plug in infinity, wherever we see an x, a number over infinity goes to 0, And so we're left to here with 2 over 5. So there's a case where it goes to one number. We had a case, well, I guess 0 is one number too. Case where it's going to the x-axis. And then let's look at one other case. How about the limit is x is going to infinity of x squared minus 1 all over x. So in this case, this is infinity over infinity. If I think of it as the highest power in the denominator is just 1. And if I went through and I multiplied everything through by 1 over x in the numerator, 1 over x in the denominator, well, x squared times 1 over x, that's going to just give me a single x minus 1 over x, sorry, minus 1 times 1 over x, which is 1 over x, all over 1 over x times x is 1. And so notice here, as x is going to infinity, our numerator is equal to infinity minus 1 over infinity. That piece goes to 0. So this limit doesn't exist, but I know that it's shooting off to positive infinity as x goes to infinity. So my end behavior of the graph, as x is getting larger and larger, is going upwards, shooting upwards, is what that's telling me. Okay, so there was a great question that as limit as x goes to infinity, do we always divide by that variable to the highest power, which is correct. There was one other way that we looked at this when we were looking at it in terms of horizontal asymptote, and does it have a horizontal asymptote or not? Horizontal asymptotes occur depending on the degree of the numerator and denominator. If the degree of the denominator was larger, so in this first example, that degree of the denominator was larger, it's always going to go off to 0. If the degrees were the same, in my case, the degrees are the same on that second example, then it's going to go off to the leading coefficient, so the number in front of that variable to the highest power in the numerator, which is 2, all over the leading coefficient of the denominator, that or number in front of the variable to the highest power in the denominator. So in this case, 2/5. In the last example, we have an example where the degree of the numerator was larger than the denominator, which is 1. And that's a case, it doesn't have a horizontal asymptote, which we saw here. It's going off to infinity. Okay, so we just talked about limits at infinity. And now finding limits at infinity, which we just did some examples. It says if f of x is p of x over q of x for polynomials p of x and q of x, we say that the limit as x goes to infinity of f of x and the limit as x goes to infinity, negative infinity of f of x can be found by dividing p of x and q of x, both the numerator and denominator, by the highest power of x in q of x. And that was what we were doing on those last 3 examples. Okay, so continuity was another major point that we looked at. Sorry. And in order for it to be continuous at some value x equals c, 3 things have to hold true. F of c is defined. So when x equals c, we do have a y value on the graph, or it exists, it's in the domain. The limit as x goes to c of f of x exists. And we talked about limits existing, meaning that the limit as x approaches c on the left of f of x has to equal the limit as x approaches c on the right of f of x. So if we can show that those are the same, then we can say the limit exists. And then we have the limit as x approaches c of f of x has to equal what f of c was. So you'll have different problems where you're either looking at a graph and saying where is it discontinuous, or you might have problems given an equation asking where it's continuous or discontinuous. And you might be given a piecewise function where you have multiple equations for that function defined at different domains, each equation, and then finding if it's continuous or not continuous and where. Okay, so given this function f of x, we want to find the values where this function is discontinuous. And so we're given a rational function, 7 minus 3x all over 1 minus x all times 3 plus x. If you have a rational function, it's discontinuous at values which set our denominator equals 0. It's undefined there. And so if it's undefined at those values, then it's not gonna, the graph is gonna have to jump. It's either gonna have asymptotes or a jump in the graph. And so looking at this, setting this value of my denominator equal to 0, I'm looking at when is 1 minus x all times 3 plus x equal to 0. Well, this is already factored. And so when we have factors equal to 0, then we can set each factor equal to 0. So we can look at when is 1 minus x equal to 0 and when is 3 plus x equal to 0. Well, 1 minus x is equal to 0. If I add x to both sides, I get 1 equals x, or x equals 1. And here, if I subtract 3 on both sides, I get x is equal to -3. Okay, so these values right here, f of x is undefined. So in order for it to be continuous, remember it had to be defined at that value of x. And so we can say that f of x is not continuous at x equals 1 and -3. That first condition didn't hold. That f of a value was not defined. So we just said that they were undefined there, but let's look at the limit as x approaches 1 on the left and the right. So if we were looking at the limit as x approaches 1 on the left-hand side of 1 of this function, 7 minus 3x all over 1 minus x, that quantity times the quantity 3 plus x in the denominator. So if I went in here and I plugged in 1, I would see right away with direct substitution, which is usually what we want to try. Notice that in the numerator, I get 7 minus 3 times 1 all over 1 minus 1 all times 3 plus 1. And so notice I get 7 minus 3 in the numerator, which is 4, all over 0 times 4. This is 4 over 0. If we get 0 in the denominator and not in the numerator, we can say that the limit does not exist. We already knew that though, because it was undefined. So let's look at what's happening though, as we're getting closer and closer to 1 on the left-hand side. And so let's kind of get some reasoning down. Is this going to blow up to positive infinity, or is it going to go down to negative infinity? So if I'm choosing a number that is close to 1, it's going to be smaller than 1. And so if I take 7 minus 3 times a number close to 1, that is going to be a positive number. So in the numerator, I know my number is positive. Well, if I have 1 minus a number that's smaller than 1, 1 minus number smaller than 1 is also positive. And 3 plus a number smaller than 1 is also positive. So thinking about it, if my numerator is positive and my denominator is both positive, then this is going to be going to positive infinity. Or if I looked at the limit as x approaches 1 on the right-hand side, let's see if it's blowing up or if it's shooting downwards as we approach 1. And so I'm going to do the same sort of reasoning, but this time, because I'm coming in on the right-hand side, my values of x are bigger than 1, close to 1, but bigger than 1. Okay, so if I'm plugging in a number close to 1 and multiplying it by 3 and subtracting from 7, that's still a positive number. So I got a positive number here all over 1 minus a number that's a little bit bigger than 1 is going to be a negative number. And 3 plus a number that's close to 1 is also going to be, there is going to be positive. And so in this case, we have positive number in the numerator, negative number in the denominator. So as x is approaching 1 on the right-hand side, this graph is shooting downwards. So I know I have a vertical asymptote here because it's undefined. My numerator is not equal to, and denominator do not equal 0 at 1. So the graph's going to look something like this. So I could do the same thing at x equals -3. I could see plugging in numbers on the left and plugging in numbers on the right. Are these going to give me positive numbers in the numerator or negative number in the numerator, positive or negative in the denominator? And so we're going to be using these techniques when we get, I think it might be the next chapter, to help us graph these functions. So looking at limits to help us graph, and then looking at derivatives to help us graph. So now looking at the example, f of x equals x squared minus 9 all over x plus 3. Again, trying to find where it's discontinuous and if the limit exists, where it is discontinuous. So again, it's discontinuous if we have a rational function wherever the denominator is equal to 0. And so I can see x plus 3 equals 0 when x is -3. Okay, so this is not in our domain, it's undefined there. And so this is where it's discontinuous. F of x is undefined at x equals 3. If we go back in here though, and we looked at the limit as x was approaching 3, -3. We're looking at the limit as x is approaching -3 of this function x squared minus 9 all over x plus 3. And we went in and we plugged in 3 wherever we saw an x. Notice here we would get 3 squared minus 9 all over 3 minus 3, so -3 plus 3. This should be -3 squared. So plugging in -3 wherever we saw an x, well, -3 quantity squared is 9. 9 minus 9 is 0, and -3 plus 3 is 0. So we got that 0 over 0, which was that indeterminate form. It didn't tell us anything. But look at the limit as x goes to -3. This is where we had to manipulate this function. And I noticed that that is factorable in the numerator. X squared minus 9. Difference of squares is x plus 3, x minus 3. All over our denominator, which is x plus 3. And so notice we have like factors in the numerator denominator, those cancel. And so now we can look at the limit as x approaches -3 of x minus 3. And if we go in here and we plug in -3 wherever we see an x, we get -3, then minus the 3. Well, -3 minus 3 is -6. So here's the case where our limit exists, but it's not continuous there. We have actually an open circle at x equals -3 and y equals -6. So this would be a case where we have a removable discontinuity. If we added that point with that function, then it would be continuous there. The other example that we looked at with the vertical asymptotes at the value where it's discontinuous is not removable. So the other thing that we looked at was the average rate of change. So the average rate of change was looking at 2 points on a function and then finding the slope of the line that connected those 2 points. So the average rate of change of f of x with respect to x as x changes from a to b is the change in your y value, f of b minus f of a, all over the change in your x value, b minus a. We took this difference quotient, which was basically we were trying to choose 2 points that were pretty much right on top of each other, getting infinitesimally close. And that's where we looked at f of x plus h minus f of x all over h. And to get that instantaneous rate of change, we let that limit h go to 0. We found that that gave us the instantaneous rate of change at that value x equals a, if we had some value. It also gave us the slope of the tangent line if we were looking at some value, or the derivative of our function or derivative at a particular point. Sometimes I feel like we had 5 sections in here. So I don't know why I didn't bring in 5 things. Hold on. So you had key terms in these sections that you should know, and we were just talking about a lot of this. And so 3.1, you should know what a limit is. You should know what a limit is from left to right. You should know 1 or 2-sided limits. Piecewise functions, limit and at infinity. 3.2, we talked about continuous, discontinuous, having removable discontinuity. Not all of the discontinuous functions at a particular value are removable. Continuous on an open and closed interval, continuous from left to right, intermediate value theorem. Don't worry too much about that. And we haven't talked about that quite yet today. But don't be too concerned about this. We'll get, I think, more into this later on in the book. 3.3, average rate of change, the difference quotient, instantaneous rate of change, and velocity. Velocity is another word for instantaneous rate of change. 3.4, we talked about secant lines. So that was the 2 points of the line that joined the 2 points, given the average rate of change between those 2 points. Tangent line was the line that had the instantaneous rate of change at a particular point and at the slope of a curve. Derivative, differentiable, and differentiation. Okay, so let's look at some limits. You need to be able to look at a graph and find limits. And in this case, it's asking us to find the limit as x is approaching -3. And because I see this little negative sign up here, that's telling me I'm coming into the left of -3. So first thing I would do when I'm looking at a limit and trying to find the limit of a graph, I go to the graph and I look at the x value I'm trying to approach. In this case, it's -3. So I'm right here. And then because it's asking me for the limit as I'm coming in on the left-hand side, I go to the piece of the graph of the left of it, and I follow it up to see, is that going to 1 y value? As I get my x values closer and closer here, my y values, right, are getting closer and closer to 4. And so the limit as x is approaching -3 on the left, this one is equal to +4. So B says, let's look at the limit as x is approaching -3, but I have a plus up here. And so that's telling me to come in on the right-hand side. So again, locate where -3 is on the graph, coming closer and closer to -3. So using that piece of the graph on the right-hand side of -3, the y value that we're getting closer and closer to is also 4. So if the left-hand side and the right-hand side are the same, then we say that the limit is equal to what they were both approaching 4. This has a closed circle here, and it is defined then. And I can say f of -3 is equal to 4. It might have asked you, is the graph continuous at x equals -3? And if it asked us, can we show that it's continuous at x equals -3? We would show that the limit exists, which we did. Left hand equals the right hand. We would show that f of -3 was defined, gives us back a y value, and that y value was the same. So looking at the next piece, it's asking me to find the limit as x is approaching -1. So find -1 on the graph. And it's coming in on the left of this g of x function. So I go to the piece of the left of -1, which is here, and I'm looking at what is the y value I'm getting closer and closer to. And notice that y value I'm getting closer and closer to is -2. So this is equal to -2. Where if I'm coming in on the right-hand side of -1, I'd be using this graph, even though it has an open circle and it's not defined there at 2, it's getting closer and closer to that y value of 2. So like 2.1, 2.01, 2.001. It's getting closer and closer to that. So we say that limit does exist and it's equal to 2. I'm sorry, the right-hand side exists and it's equal to 2. When it asks if the limit exists, though, as x approaches -1, it doesn't exist. And it doesn't exist because our y value that we're approaching on the left is not equal to the y value we get on the right. G of -1. So looking when x is -1, we want to look at the piece of the graph where we have a solid circle. And the piece of graph at x equals -1 where we have the solid circles right here. And so g of -1, my y value is -2. And it's discontinuous because our limit doesn't exist. Okay, so let's just go through these really quickly. So we're looking at the limit here as x is approaching 4 on the left of f of x. So let's go to x equals 4. I notice right there that that's a vertical asymptote. On the left, even though the limit doesn't exist, I know that this is shooting up, going up to +infinity as we get closer and closer to x equals 4 on the left. So I would say that this is equal to +infinity. As we're approaching x equals 4 on the right-hand side, though, notice this graph is shooting downwards. This is going to -infinity. The limit as x approaches 4, this does not exist. And f of 4, this is a vertical asymptote. This is undefined. There's no value of x equals 4. So the next one, you're looking at the limit as x approaches 2 on the left, the right, the limit as x approaches 2 of h of x and h of 2. So notice as x is approaching 2 on the left, even though this is an open circle here, my y value is getting closer and closer to 1. As x approaches 2 on the right, my y value still is getting closer and closer to 1. Left hand and right hand are the same, so my limit as x approaches 2 of h of x is 1. The thing here for h of 2 is, notice this is not a solid circle, and there's no point above or below this x equals 2 at 1. And so this is undefined. You should be able to look at graphs as x goes to infinity and negative infinity and see what's happening. So looking at the graph of g of x here, as x is approaching negative infinity. Well, x is going to negative infinity. We're trying to look at the graph to see what is our y value doing. Well, this is going upwards forever. So this is going to positive infinity. In this case, we're looking 22 as x is approaching infinity. X is going to infinity. Is there any particular y value that we're getting closer and closer to? It's showing me there's a horizontal asymptote here. So this graph is getting closer and closer to this horizontal line, y equals -3. So this is equal to -3. Okay, so now we're looking at limits, reviewing limits, and what do we do when we get that indeterminate form 0 over 0? And so if you get that form, there are a couple of things that you need to try. It just kind of depends on what that rational function looks like, but factoring is always good. If you have a radical in there and somewhere in the numerator denominator, either rationalizing that numerator denominator that was multiplying by that conjugate, or if you have a complex fraction, get rid of the complex fraction, get rid of those fractions within a fraction. And so looking at this example, this first one, let's just do is the limit as x is approaching 0 of -1 all over x plus 2, then plus 1/2, and then those two fractions are all over x. If we go in here, and that's really what you really want to do, because there might be one in there, couple of them in there that you can just do direct substitution and it might fall out. And I guess that's what we do at the end anyway. So here we would have -1 all over 0 plus 2 plus 1/2 all over 0. And so when I do this, I notice I have -1/2 plus 1/2 in the numerator. We get this 0 all over 0. Indeterminate form, I can't say that this limit doesn't exist. I need to go back and manipulate it. And so there's a couple ways that you can deal with complex fractions. I tend to like to look at all the denominators of the fractions within that main fraction and find my LCD. Once you find your LCD, if we multiply by the LCD divided by the LCD, that fancy fraction or fancy one, that would clear all the fractions within here. So looking at my first fraction within the fraction, I have x plus 2. Looking at the other denominator, I have 2 and x plus 2, they don't have any common factors. And so my LCD is going to be x plus 2 all times 2. So I'm going to multiply that by to each term in the numerator and each term in the denominator. And so when we distribute this here, we get this limit as x goes to 0 of this -1 all over x plus 2 all times this x plus 2 times 2. Then we have this plus 1/2. We also have to distribute it to the second grouping in the numerator. So that's all times x plus 2 times 2. All divided by our denominator x, all times the LCD. I'm going to put the 2 in front. 2 times x plus 2. So notice, and this was the whole point of multiplying by the LCD, was to clear the fractions within the fraction. And so notice this x plus 2 cancels with this x plus 2. And so we're left with, bring down the limit, because we haven't taken the limit yet. -1 times 2 here. So that first piece, we are left with -2. Then we have this plus 1/2 times this quantity. And so notice here, we have a 2 in common in the numerator and denominator. And all you're left with is this x plus 2. Because there's no coefficient in front of here other than 1, I can drop those parentheses. There was a negative in here, I couldn't drop that parentheses. All over, and I'm not going to distribute this piece. I'm going to just leave it as 2x times x plus 2. So right away, I see that the numerator, there's like terms that 2 and -2 cancels. And so we have the limit as x is approaching 0. -2 plus 2 cancels, we're left with x in the numerator, all over 2x times x plus 2. So now we have a common factor in the numerator denominator, which cancel. And so we have x in the numerator, x in the denominator, they cancel. I don't like that, that always pulls up. And then we have the limit as x approaches 0 of 1 all over 2 times the quantity x plus 2. So now we can go in, do our direct substitution, plug in 0 wherever we see an x, and we get 1 all over 2 times, well, 0 plus 2 is 2, which is 1/4. So the limit as x is approaching 0 of that complex fraction gives us back 1/4. Okay, so this is another limit that you might get where you get an indeterminate form. So notice this limit as x approaches 16. If we plug in 16 wherever we see an x, we got the square root of 16, which is 4, minus that 4 in our numerator, which is 0. And then plugging in 16 in the denominator, we get 16 minus 16, which is also 0. So indeterminate form doesn't tell me anything. I need to go manipulate this. It's rational and I have a radical. So to deal with that, you're going to clear the radical, and we can do that by multiplying through by our fancy one. Square root of x conjugate of the square root of x plus 4 is the square root of x. That is the conjugate of the square root of x minus 4. So we're going to multiply both top and bottom by the square root of x plus 4. So we can FOIL out square root of x minus 4 times the square root of x plus 4, or notice that that is just a difference of squares, which is the same thing as squaring our first term. So squaring our square root of x minus squaring our second term. When we distributed that out, the middle term would have canceled. And we're not going to distribute the piece that we're not getting rid of the radical, that doesn't have the radical. So if we do this, the square root of x quantity squared is x, minus the square root of 4 squared is 16, all over x minus 16, that times the square root of x plus 4. Bring down our limit. So now notice that once we've rationalized that numerator, we have like factors in the numerator denominator, so we can cancel this x minus 16, and we're left with the limit x approaches 16 of 1 over the square root of x plus 4. So direct substitution, we have 1 all over the square root of 16 plus 4. Well, the square root of 16 is 4. So we have 1 all over 4 plus 4, or 1/8. Okay, so the next one you guys asked about was, sorry. The limit as x is approaching -infinity of 3/8 And then we're going to have plus 3 over x. And then minus 6 over x squared. So if we go in and we do direct substitution and plug in infinity wherever we see an x, I notice that these second two terms, 3 over x and minus 6 over x squared, as x goes to infinity, that was that rule that piece goes to 0. So 3 over x would go to 0 and minus 6 over x squared would also go to 0. And so we would just be left with the first term, 3/8. So graphically, what's happening there is x is going to negative infinity, even positive infinity. We have a horizontal asymptote, a horizontal line at 3/8 that the graph is getting closer and closer to. Okay, so we have a following piecewise function. It's asked us to graph it, find any discontinuity, find the left and right limits of any discontinuity. Our first equation is 4x plus 4, and those are values for x is less than or equal to 0. So we want to graph that equation. I notice 4x plus 4 is a line. I can tell what the slope is. It's in the form y equals mx plus b. Our slope is 4, and my y-intercept is also 4. And so you can plot points if you want, but you just need to make sure that you're staying within this domain. You're only choosing values of x less than or equal to 0. The only other time that you would not stay in the domain is when you're looking at the n values of our inequality. So 0 for the second equation is not part of that domain, but we have to see what's happening at 0 because we're getting really, really close to that value. So when x is 0, we would use the first equation, plugging it in, I see my y value is 4. This is included because I have the equal sign here, so I'm going to put a close circle at 0, 4. Choosing numbers less than 0, so if I plugged in -1, 4 times -1 is -4 plus 4 is 0. And so at -1, x is -1, my y value is 0. I know this is a line, so I'm just going to connect a line going through here. And I know it's for all values of x less than 0. So it's everything to the left of 0. So now I'm going to graph the other equation. Looking at it, I can see that it's a quadratic. And I want to see what's happening at x equals 0, even though that's not part of the domain. If I go in here and I plug in 0 in here, for x, I get 0 squared minus 4 times 0, still 0, plus 4 is 4. So when x is 0, y is equal to 4. Because of this piece, I would normally put an open circle there. But if I go to my graph, I graph that first equation, I already have a point there at 0, 4. And so this open circle ends up being closed because of that other equation. I can now start plugging in values which are greater than 0. So if I plugged in 1, I get 1 squared minus 4 plus 4. Well, that would give me back 1. So when x is 1, y is 1. I can plug in another value. If I plugged in 2 there, 2 squared is 4, minus 4 times 2, that's 8, plus 4, I get, this is 0. And so when I draw this piece, the second equation, I do not want to extend the second equation to the left of 0 because it's not defined there. And I want to graph this. This is a parabola, I know, and so I should be able to find that vertex. So really quickly, and I don't really want to spend too much time on that, but I know a vertex, there's a couple ways I can do that. I can put it in vertex form, or the vertex is at -b all over 2a, and then f of, or h of in our case, -b over 2a. Where our quadratic is in the form of a times x squared plus bx plus c. So negative b, I just need to know where this is changing direction. My negative b, negative of -4 is 4, all over 2 times a, which is 1. So 4 over 2 is 2. And so if I look at h of 2, well, I already did that work here. I found that that was 0. This is the place where it's going to change direction to 0 is equal to the vertex. So we kind of give an accurate graph. So this will be going upwards forever. And so only point that we might have a problem where it would be discontinuous would be at where our inequalities are changing, where our equations are changing. And so in this case, there was only one place when x was equal to 0. Because we have that same y value, it's continuous there. So this is continuous everywhere. And I know polynomials are always continuous. So 4x plus 4 is continuous and x squared minus 4x is always continuous. So I don't have any problems when x is less than 0 or greater than 0. And I wanted us to look at this limit as x goes to 0 of f of x. Well, approaching on the left as we get closer and closer to 0, x gets closer and closer to 0, my y value is 4, and the right, it's also 4. You should also be able to look at a piecewise function and find some value k to make your piecewise function continuous. And so let's say you had h of x. This is equal to x squared minus x minus 15 all over x minus 3. And this is the case if x does not equal 3. We have another function though, and this is when x is equal to 3. That is k times x minus 1. If x equals 3. Okay, so we want to find k to make this, if possible, h of x a continuous function everywhere. So the only problem I would have for that first equation is x equals 3. That makes my denominator equal to 0. I'm curious though, if I factored that numerator, if I have a factor of x minus 3. So we might want to rewrite this. Let's look at 2x squared minus x minus 15. So if I look at this, 2 times negative 15 is negative 30. There's two numbers that multiply to negative 30 and add to negative 6. So I know that this is factorable. Let's think about it. If this was x minus 3, in order to get this first term 2x squared, I would need a 2x here. And in order to make this a negative 15 at the end, I need a positive 5 here. So let's just make sure that this equals if I distribute it out, the thing above. So this is 2x squared plus 5x minus 6x. Well, 5x minus 6x is negative x, and negative 3 times 15. Okay, so that does factor. We're going to have to do this anyway. So this is x minus 3 all over 2x plus 5 all over x minus 3. X doesn't equal 3. And it's k times x minus 1 if x equals 3. Well, let's look at h of 3. Well, when x is 3, it tells me to use this equation. So it says go in here and plug in 3 wherever you see an x. So doing that, I have k times 3 minus 1. Or I'm going to write it as 3k minus 1. In order for this to be continuous, this y value for this equation has to be the same y value as x is approaching 3 on the left and the right. Well, if we looked at the limit as x is approaching 3, well, if you're approaching 3 on the left, something smaller than 3, I use this equation, first equation, x minus 3, all times 2x plus 5, all over x minus 3. If I'm approaching 3 on the right, it's a value bigger than 3, it's not 3, it's just getting closer to 3. I'd also be using that first equation. If I plugged in 3, I would get a indeterminate form. We factored it, so those cancel. Now we can go do direct substitution and we get 2 times 3 plus 5. So this is equal to 6 plus 5, which is equal to 11. So in order for the limit to exist, or actually it exists, but in order for it to be continuous, remember that limit as x is approaching 3 has to equal of h of x has to equal h of 3. Well, we found that this limit as x is approaching 3, that was this 11, has to equal, well, we saw h of 3 was 3k minus 1. So all we have to do here is now solve for k. So if we added 1 to both sides, let's isolate k, we get 12 equals 3k. Divide both sides by 3, we get k is 4.
Professor,
Yeah.
can you zoom out a little?
Yep. Yep. There you go. So we haven't had a chance to do them, and you need to be able to do this, but you need to be able to find this equation of a secant line. You need to be able to find the average rate of change between 2 points, which is what you need to find in order to find that equation of the secant line. You need to be able to find the instantaneous rate of change at a particular x value. You need to be able to find the tangent line going through that point with that instantaneous rate of change. You're going to need to be able to find the derivative using the formal definition, or the definition of derivative. That limit is h goes to 0 of the quotient rule. You also are going to need to be able to match graphs of a function and the derivative function. So those are things that we haven't been able to touch on in this review. It's hard to go through an hour and 50 minutes of all the material. It took us 6 weeks to go through. So I will stick behind during office hours and continue recording, so you guys have some more examples if you want to refer to them, and you're welcome to stay and ask questions. If not, you can leave. You might have classes or something else, work that you need to go to, but you can always come back and watch this video, the rest of it later. Okay, so looking at f of x equals x cubed, we want to find the derivative using the definition of a derivative. And so we're going to look at the limit as h approaches 0. This is the definition of f of x plus h minus f of x all over h. And so the first piece, when we're looking at the limit, and this is, we can define this as f prime of x equals limit as h goes to 0. So wherever we see an x, this is telling me to go back into my function and plug in that piece, x plus h. So I'm going to have x plus h, and then I'm going to cube it, minus my f of x function. Well, my f of x function is x cubed, so minus x cubed all over h. So distributing out x plus h times x plus h quantity cubed can get a little tedious and a little messy. So let's just kind of do that on the side real quick. So x plus h quantity cubed is saying we're going to multiply x plus h times x plus h times x plus h. So let's first distribute out x plus h times x plus h. And as we do that, x times x is x squared, x times h, so this plus an xh. Now let's distribute this h. So we have h times x, so that's plus, I'm going to write it as xh. H times h, so plus h squared. We have this whole parentheses times, we still have this x plus h here. Let's combine like terms in that first parentheses before we distribute. So I have x squared, well, an xh plus an xh is plus a 2xh plus an h squared, all times x plus h. So distributing here, x squared times x, x cubed, x squared times h, so that's plus a hx squared. So now taking 2xh and distributing it to each term. So plus 2xh times x, so that's a 2x squared h. And 2xh plus times h, so that's a 2xh squared. And now let's distribute the h squared. So h squared times x, so that's plus xh squared. And h squared times h, so plus h cubed. I would go through here to see if I had any like terms. So an h with an x squared. Here's a h with an x squared. And that was the only piece. So I have an x cubed plus 1hx squared plus 2, that's 3hx squared. I have a 2xh squared and a 1xh squared, that's a 3xh squared plus h cubed. So that was just this x plus h quantity cube piece. So we're looking at the limit as h is going to 0 of x plus h cubed, which is x cubed plus 3hx squared plus 3xh squared plus h cubed minus x cubed all over h. So notice x cubed and negative x cubed cancels. And then notice the three terms that are left in our numerator all have a factor of h in common. And so we could pull out an h and we would have 3x squared left for this first term. We would have plus 3xh plus h squared all over h. Still have the limit as h goes to 0. So our h's cancel here. And so now when we go in and we plug in 0 wherever we see an x, not an x, an h, this would give us back 3x squared plus, well, 3 times x times 0 is 0 plus 0 squared is 0. So we found that the derivative of our function f of x is equal to 3x squared by that formal definition. So I know we looked at this yesterday, Tuesday, by using the general power rule, bringing our power down front, bringing that 3 down front, and subtracting 1 from our power, notice is 3x squared. But for this exam, or unless I tell you use a formal definition on a test question when you're in class, you have to, for this exam, you have to use that formal definition. Later.
I'm sorry for
Okay, so there was a question on how I got this h down here. And so let me just kind of talk about it real quick. Notice that the 3 terms left after our x cubed canceled all had a single, at least one h in it. If we did our direct substitution and plugged in 0 wherever we saw an h, we would have gotten that indeterminate form. And so I just didn't show this up. Like I factored the h out of those 3 terms, and that's where I was left with this. I did that so I wouldn't have that indeterminate form. And one of the tips was to factor. And notice now our h's cancel, and then we didn't have the indeterminate form. So that typically happens when you're using the formal definition of the derivative. You're going to be able to manipulate it so you don't get that 0/0 form. And you'll be able to factor out an h and cancel. So let's extend this further. Let's find the derivative at a particular value. So there's a couple ways that they could ask you to do this. They could say, well, find the derivative of f of x when x is equal to 2. Find f prime of 2. They might ask you to find the equation of the tangent line when x is 2. So let's do that. So let's say find the equation of the tangent line at x equals 2 on f of x equals x cubed. And so to find the equation of the tangent line, we need the slope when x is 2. When we already did this work up here. And so let's find f prime of 2. So our tangent line, our slope is going to equal to, in this case, f prime of 2. And so if we go into our derivative function, 3x squared, and we plugged in 2 wherever we saw an x there, we would have 3 times 2 quantity squared. So 2 squared is 4, so 3 times 4 gives us 12. So I know that the slope of my tangent line is 12. So I need one other thing when I'm finding an equation of a line. I need a point. So I need a slope and a point. Well, we can find a point on that line by looking at f of the x value we're trying to find the equation of the tangent line at. So f of 2. So if I plug it back into my original function, I get 2 cubed, which is 8. So I have a point at 2, 8. So given a point at 2, 8 and the slope of 12, I can find the equation line by either using my point slope formula, y minus y sub 1 equals m times the quantity x minus x sub 1, or let's just solve for b by plugging in what we know and then go back in and plug in our slope in b. So y is 8 is equal to my slope, which is 12 times x, which is 2 plus b. So 8 equals 24 plus b. If I subtract 24 on both sides, 8 minus 24 is negative 16. So with that, my y-intercept negative 16 and my slope 12, I now know the equation of the tangent line is y equals my slope 12 times x minus 16. Okay, so similarly, you should be able to find the equation of a secant line. So maybe it said find the equation of the secant line through when a is equal to 2 and b is equal to, let's say, 4. The only difference here is that we would look at our points. We would look at what is f of 2. What we already found that was 8. And what is f of 4? So if I cube 4, well, 4 times 4 is 16. 16 times 4 is 64. So I have a point at 2, 8, and I have a point at 464. I'd have to find the slope with those 2 points. So the change in y, 64 minus 8, all over the change in x, 4 minus 2. Well, 64 minus 8, that is 56 divided by 2. Well, 2 goes into 5 twice, leaving me 1. 2 goes into 16 8 times. So I would have a slope of 28, and then I'd have to choose one of those points. And so it doesn't matter which one I choose. I like the smaller number, so I would choose maybe 2, 8. And so I could go in here, my y value is equal to 8 equals my slope 28 times x, which is 2 plus b. 8 is equal to 28 times 2 is 56 plus b. Subtract 56 on both sides, I get b is negative what is that? 48. So my equation of the secant line, that would be y equals my slope, 28 times x plus b, so minus 48. If it just said find the average rate of change of f of x between 2 and 4, we would have just stopped here. So I just want to go over a couple more examples of just using the formal definition, because you need to use that of the derivative to find the derivative. So let's find f prime of x if we're given f of x is 1 over x. And so again, we're looking at the limit, h goes to 0 of f of x plus h minus f of x all over h. So if I go in here and I plug in x plus h, wherever I see an x in my original function 1 over x, I get 1 over x plus h minus my f of x function, which is 1 over x. And then I'm putting this all over h. And so now if I went and did direct substitution, I get 0 over 0. Don't want that. And so I need to manipulate this. So this was an example where we had a complex fraction. And one way to manipulate that is to get rid of the complex fraction is multiplying by the LCD, least common denominator of the fractions within that fraction. And so multiplying through by x times x plus h, that's going to clear our fractions in the numerator. And so we're left with a limit as x goes to 0. Well, 1 over x plus h times x, all times x plus h, those x plus h cancels, leaving you with x minus. When we distribute this to 1 over x, x's cancel, and we're left with x plus h. We have to be careful here because there's a minus. I need to keep those parentheses, x plus h. All over, let's just leave it as h times x plus h. So notice now if I distribute my negative sign, I have the limit as h goes to 0. For some reason I reverted to x here, but those should be h's. X minus h all over h times x plus h. So notice that my x's cancel, x minus x. Notice that I am left with one term in the numerator, and I have a factor of h in there, which can cancel with a factor of h in the denominator. And so if I cancel those h's, I'm left with a limit as h goes to 0 of -1 all over x all over times x plus h. So as h is going to 0, plugging in 0 wherever I see an h, I'm left with -1 in my numerator all over x times x, or x squared. So the derivative of 1 over x is -1 over x squared. So one other type I want to go through, and then I'll stop. F of x equals the square root of x, and using the formal definition to find the derivative. So if we're given f of x is equal to the square root of x, and we want to find f prime of x. So I'm looking at the limit as h goes to 0. I'm plugging in x plus h wherever I see an x. So the square root of x plus h minus f of x, which is the square root of x, all over h. So I notice again, if I go in here, do direct substitution, I get 0 in the numerator, 0 in the denominator, indeterminate form, I got to manipulate it. Well, this has radicals in it. So one way to manipulate it is to multiply through by the conjugate of those radicals. And so in that case, and I'm going to use that as my fancy one. So I'm going to look at the square root of x plus h, change the sign in between the radicals, plus the square root of x all over the square root of x plus h, plus the square root of x. So now I have the limit, h goes to 0. Difference of squares in the numerator. So if I square my square root of x plus h, that gives me x plus h, minus square root of x quantity squared is x all over my denominator. So h times parentheses square root of x plus h, and then plus the square root of x. So again, those terms that don't have the h cancel out, x minus x cancel. I'm left with just h in the numerator. I have a single h in the denominator. They're like terms, those are going to cancel. And so we're left here with a limit as h is approaching 0 of 1 all over the square root of x plus h plus the square root of x. So if we do direct substitution now and we plug in 0 wherever we see an h, this would equal 1 over the square root of x plus the square root of x. Those are like terms in the denominator. So 1 square root of x plus 1 square root of x is 2 square roots of x. So we found the derivative of the square root of x to be 1 over 2 times the square root of x by using the formal definition. So you should also be able to do graphs of derivatives. We spent a lot of time on that on Tuesday, so that was a good review. And then also looking at some application. So if they ask you for marginal profit, marginal cost, marginal revenue, you're looking at the derivative of that function. If they're asking for rate of change or instantaneous rate of change, velocity, then it depends. Velocity, instantaneous rate of change is the derivative. Okay, so hopefully that review was helpful. And let me know if you have any questions.